All right, so we are going to continue talking about exponential and logistic functions. Exponential growth and decay. It says for any exponential function f of x equals a times b to the x and any real number x, then f of x plus 1 equals b times f of x. I don't really know what this is about, but what you need to know is if a is greater than 0, okay, and b is greater than 0, then you're going to have a growth factor. If a is greater than 0 and b is not less than 0, they don't mean negative. They mean between 0 and 1, because remember, b can't be negative. Okay, but if b is between 0 and 1, meaning like a half or 2/3 or some sort of a fraction, okay, then you're going to have decay. All right, so it says state whether the function is an exponential growth function or an exponential decay function and describe its end behavior using limits. Excuse me. All right, well, my a would be 1. I mean, because if I rewrote this as a times b to the x, this has to be my b, which means if they're not writing it, they're multiplying by 1. So b would be 0.2. And you got to look. Either b is greater than 1 or it's between 0 and 1. And 0.2 is between 0 and 1, which means that this is decay. If it's decay, and I'm kind of cheating here a little bit, but no, I won't. If it's decay, it's going to come down like this. So it's going to go through 0a, which in this case is 1, and 1b. So it would go through 1 comma 0.2, which is right there. So this function is going to do this. We don't really need the, well, we do, but we need to describe its end behavior using limits. Well, the limit as x approaches negative infinity, my function, so if here's negative infinity is this way, not 8, negative infinity. This is the arrow closest to infinity, and it's pointing up, so the function is going to infinity. The limit as x approaches positive infinity, this way is positive infinity. The arrow closest to that is this one, and it's getting closer and closer and closer to this, to the axis, and but it's not going to cross it. So we say the function is approaching 0. Okay? All right, so you do this one. Hit pause, come back when you're ready. Hopefully you got 2. Okay, so in this case, again, I could rewrite this as 1 times 6 to the negative x. Yes? What the heck does that mean? Well, remember that little trick. Not 1.6, that's 1 times. This would be 1 times 6 to the negative first to the x, yes? So if I look at this, that would be 1 over 6 to the x, which means my base is 1/6, which means it's between 0 and 1, which means it's decay, which means it comes down like this, yes? And it would actually go through 0, 1, and 1 comma 1/6, which is like that. So it comes down like this. And so again, as x goes to negative infinity, my function's pointing up. As x goes to positive infinity, that arrow is getting closer and closer to 0. Okay? All right, logistic growth functions. Logistic growth functions are pretty interesting. It says let a, b, c, and k be positive constants with b less than 1. And what they mean b less than 1 is, again, a fraction. A logistic growth function in x is a function that can be written in this form. F of x equals c over 1 plus a times b to the x. And they also have this e to the negative kx. And remember, that's just a constant 2.7. 1 something. Okay? Now, what's really cool about this is that the mother of all logistic functions, what happens on logistic functions is you always get this S-looking shape, but it always is between 2 asymptotes. And one of them is always the x-axis, okay? Y equals 0. And then the other one is wherever the top goes. and you can tell where the top goes. Well, I'll show you that in a second. But at any rate, you've got these two horizontal asymptotes, and the graph makes this S shape between those two horizontal asymptotes. All right, so here we go. We're going to graph these functions. And here's how you figure out how high it goes, okay? You got to find the y-intercept and the horizontal asymptotes, okay? So you need the y-intercept, so I'm going to find f of 0. F of 0 would be 8 over 1 plus 3 times 0.7 to the 0 degree. That's just 1. So that leaves me 8 over 4, which is 2. So 0, comma 2 is going to be my y-intercept. My horizontal asymptotes, y equals 0 is always one of them. Y equals 0 is always one of them. And the other one is y equals c. Well, c is whatever's up here on top. So since it was 8, that's going to be at y equals 8. 1, 2, 3, 4, 5, 6, 7, 8. Yeah? And so then what you do is you sketch your S shape through the point between the asymptotes. So this thing is going to go asymptotic to the asymptote, obviously. It's going to pass through this y-intercept, and then it's going to come up there to its maximum growth. Okay? All right, so if I do one with E in it, again, it's no different. E is just 2.71 something. If I find f of 0, I would have 20 over 1 plus 2e to the negative 3 times 0. That's to the 0, right? I don't think I need to write every step out, but that's to the 0. Anything to the 0 degree is 1. So that gives me 20 over 3, which is 6.6 repeating. Okay? So if I do that, 1, 2, 3, 4, 5, 6, 7, 6.6 repeating is about right there. Okay, and then I need my horizontal asymptotes. One of them is always at y equals 0. And the other one is going to be at c, which is going to be y equals 20. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. That's going to be my other horizontal asymptote. And if I draw my sneaky S through it and go through the point, asymptote, through the point, and goes up. That shouldn't be like that. I don't draw so well. Alright, something like that. No, it doesn't do that, Tenzin. I can't draw. Something like that. Alright, so you do this one. Match the graph. Don't use a calculator. Hit pause, come back when you're ready. And hopefully you got 4. Alright, if not, let's look at y. To get my y-intercept, I plot y of 0, which would be 4 over 1 plus 2 times 0.6 to the 0. This is just 1, so that's 4 over 3, which is 1.6 repeating. So this is not 1.6, because that's not even halfway. This is not 1.6. It's not even halfway. That looks like 1.6, and that looks like 1.6. So it's between those two. Well, your S, guys, always goes this way unless you have those reflections, like if your fraction was negative or whatever. But it's not, so it's got to be 4. Okay, so this one says solve the inequality graphically. And what you're going to do is you're going to type this in for y1 and you're going to type this in for y2, and then you're going to see when 8 to the x is higher or bigger than 2 to the x. So I go to my graphing calculator. For y1 I typed in 8 to the x. For y2 I typed in 2 to the x. And my color one, like the color calculator, really makes seeing these easy. So what you're doing is you want to know what they're asking you is this side of the graph would be when x is less than 0, because all of these are negative x values, yes? This side of the graph is when x is greater than 0, when you have positive x's, yes? So what they want to know is where, on which side, is 8 to the x bigger than 2 to the x. So if you look at my graph, you're looking at the blue line. And you want to know basically when the blue line is higher than the red line. Okay? Well, on this side of the axis, let me get a different color. On this side of the axis, when x is less than 0, red is on top. So 2 to the x is bigger on this side because the red is on top. On this side, when x is greater than 0, do you see how blue is on top of red? Which means that 8 to the x is bigger. And we want to know when 8 to the x is bigger. And 8 to the x is bigger when x is greater than 0. And that's your answer. That's it. You're done. Okay, so let's look at a couple more. Again, the only thing that makes these a pain in the butt is you got to be real careful when you're graphing them on your graphing calculator because yours aren't in color. So you got to pay attention to which one you typed first and which one got drawn first on your graph. And I'll show you one like that in a second. Oh, sorry. Okay, so I typed them in the calculator. I typed the blue is the 1/4 to the negative x, and the red is 1/3 to the negative x. Okay? Now, notice that when x is less than 0, well, that don't show up very well. When x is less than 0, on this side, the red is on top. So 1/3 to the negative x is bigger. On this side, when x is greater than 0, blue's on top, which means 1/4 to the negative x is bigger. Now we got to figure out what they want to know. Okay, they want to know when 1/4 to the negative x is bigger. Okay, so 1/4 of the negative x is bigger on this side, which means my solution is when x is greater than 0. Okay? Alright, so you do this one. And again, I kind of, here's your kind of graphing calculator. So what I did was I typed in 3 to the negative x first, and I paid attention. It was the lower one on this side. And then I graphed 7 to the negative x second. So then I colored them. This one was yellow, this one was red. Okay? So what we're going to look at is on which side is happening what. On this side, when x is less than 0, red is on top. So 7 to the negative x would be bigger. On this side, when x is greater than 0, yellow's on top, which means 3 to the negative x is bigger on this side. And they want to know when is, basically, you can read this two different ways, inequalities. You want to know when 3 to the negative x is smaller than this one. So or you can read it backwards and you're trying to figure out when this one is the biggest. And that one's the biggest on this side. So my answer is when x is less than 0. Yeah? There you go. Okay, so try this one. Hit pause, come back when you're ready. Alright, and same thing here. You can see the yellow one I did was the 1/6 of the x, the red one was 1/4 of the x. On this side, yellow is bigger, so when x is less than 0, 1/6 to the x is bigger. When x is greater than 0, red's on top, which means 1/4 to the x is bigger. They want to know, again, if you read it this way, it says they want to know when this one is smallest or smaller. You can also read it this way, and they're asking you, when is this one bigger? Well, 1/4 of the x is bigger when x is greater than 0. All right, so how do you identify and graph logistic growth functions? Well, you need to find the y-intercept by finding f of 0. And then you need to plot your horizontal asymptotes, which is always at y equals 0 and y equals c. And then you sketch an S shape through the points. All right. Population growth application problems. It says to write exponential functions for data. You're going to use this population functions. And what it is it looks just like your exponential functions, which is y equals ab to the x. It's just that for here, your a is your initial population, which if they're giving you data, it's the y-coordinate of the earliest ordered pair. Makes sense. The first ordered pair would be the start of the population, so that would be your first y-coordinate. P of t represents the final population. That's going to be the y-coordinate of the latest ordered pair. And t is time. So if you're writing an equation, you're going to plug in P sub naught, initial population, the time, and the final population, and you're going to solve it for B. And then you plug in your initial and B, and you'll have your equation. And then to find when the population will reach a number, right now, until I teach you logarithms, which is coming next, we have no way to solve these. You guys, we've done algebra for years now, but x has always been on the ground. X is up here in the air. To solve for something up in the air, we don't have any tools yet. There's no tools to get x out of the air. How do you get x out of the air? It's called logarithms. But that's coming next. So at this point, the only choice we have to solve these equations is graphically. Because right now, we don't have the algebraic tools to solve these because you got to get x out of the air. All right, so we're going to use a graphing calculator. You're going to type in your equation you made for y1, type in the population you're trying to reach for y2, set your window to handle the data, and calculate the intersection point. So here we go. All right, it says using the data in table 3.7 and assuming the growth is exponential, when would the population of Austin surpass 800,000 persons? So we're just looking at Austin's data. We're not looking at Columbus, okay? So would you agree that for Austin, the initial population was 465,622 because that was the earliest year. The final population, P sub t, or P of t, I should say, is the latest population, which is 656,562. Yes? And time is what we're looking for. Okay? So if I wrote an equation for Austin, I've got to figure out what B is. Oh, I know time. 1990 to 2000 is 10 years. My bad. Okay, because it says we have to find B first. So I have to know P sub naught, P of t, and t. And I got them. So I'm going to plug them into this equation, which says P of t equals P sub naught times B to the t. So if I set this bad boy up, I'm going to have 656,562 equals 465,622 times B to the 10th. Yes? And I'm trying to solve this thing for B. So before I can take a root to kill it, I've got to isolate it. So I'm going to divide by 465,622. 465,622. And that gives me B to the 10th equals, in just a second, okay, 656,562 divided by 465,622, I get 1.410075125. And how you round is up to you. The longer you wait to round, the more accurate your answer will be. So now, to get rid of that, I get to get B alone, I got to get rid of that 10th degree, which means I'm going to take the 10th root. Okay, that would cancel that and gives me my B. So to type this in, you're going to type 10, hit your math key, hit choice 5, and then type 1.410075125. So if I hit 10 and hit my math key, go down to choice 5 and type in, I'm just going to do second answer, enter, and I get B equals 1.034961573. Let's just call it 1.03. So now that we have my B, I can write my equation. And when you write your equation, you only substitute in your initial and your B. This was the final population of my data. Remember, I'm actually trying to figure out when it's going to reach 800,000. Okay? So in my equation for Austin, my Austin equation is going to be P of T equals my initial population, which was 465,622. Let me give you some more room here. P of T equals 465,622 times 1.03 to the x. Okay? And again, I'm not going to put in 10. 10 was just my time for this particular set of data, and all that allowed me to do was find my base. Now, what they want to know is when will this, you now have a model to represent the population growth of Austin, Texas. So now what they want you to do is to use this model to figure out when will this population surpass 800,000 persons. So they want this to become 800,000. And like I said, in a week or so, we'll learn how to solve this algebraically. You would divide by this, and then we would have to take the log to drop the exponent out of the air. But like I said, for right now, we don't have those tools yet, so we don't have a choice but to solve it graphically. So I'm going to type this in for y1 and this in for y2. Oh, this was showing you how to type that in. Okay, so I type in that for y1 and that, I switched it. That was y1 and that was y2. It doesn't matter. And I changed my window. Okay, and you guys will get better at estimating your window the more of these you do. And it's just a matter of playing around. I mean, I knew that I was trying to get up to 800,000, so I knew my max had to be that. So I went up to 850,000, and I counted by 100,000s because that's huge. Okay, and I started at -10, although you don't really see negatives. Same with the X window. In application problems, I don't care about anything that happens over here because it doesn't make any sense in the context of my problem. You can't have negative time and you can't have negative populations, okay? So really, your window doesn't have to include the negatives. I just don't like seeing just one quadrant. So anyway, then you're going to calculate the intersection point, and your calculation gives you x equals 18.3 and y equals 800,000. And what that means is in 18.3 years, the population of Austin should surpass 800,000. Okay? Now, it asked you, it didn't say how long is it going to take, it actually asked you when, so they're wanting a year. Well, this all started in 1990. If I add 18 years, if I round to the nearest whole, if I add 18 years, I'm going to get 2008. And it'd be interesting to Google the population of Austin, Texas in the year 2008 and see how close it was to 800,000. And if it was close, that would mean that this is a really good model for Austin, Texas. If it's not close at all, that means it's a bad model. All right, so now same table, but now they want to know when Columbus will surpass 800,000 people. So we're going to do it the exact same way. My final population for my data was 711,265. My initial population for my data was 632,910. And again, my time span is 10 years for this data. So my model for this data would be 711,265 equals 632,910 times b to the 10th. So same drill. We're going to isolate b to kill it. So I'm going to divide by 632,910 on both sides. That gives me b to the 10th equals 711,265 divided by 632,910 1.123801172. To kill the 10th degree, I'm going to take the 10th root. Please, you're not taking the square root, you're taking the 10th root. So if I do, and then I typed it in your calculator for you, if I do the 10th root of that answer, I get 1.01 if I round. Okay? So my population model for Columbus would be P of T equals Ohio's initial through 632,910 times the B we just found to the X. There's my Columbus model. This models the population in Columbus, Ohio. And now what they want to know is, when will this population surpass 800,000 people? So you plug in for the final population, you just plug in 800,000 times 10.01 to the X. And again, at this point, our algebra doesn't work because you don't have those tools yet. So we got to go graphical. And you can see I typed in the first equation, 800,000 for the second, played with my window so I could see the intersection. And it says they will intersect when X is 23.5 and Y is 800,000. So if I round, this means it's going to take at least 24 years. Okay? So, yeah. Oh, when will that be? Well, 1990 plus 24 years later, 4, 9, 10, 11, 2014. In 2014, Columbus, Ohio should surpass 800,000. Again, it'd be interesting to Google that and see if that's what happened. Okay, so now it says, assuming the growth is exponential, when would the populations of Austin and Columbus be equal? Well, we already wrote our Austin and our equation, Austin and Columbus formulas. My population model for Austin was P of T equals, I'm going to have to back up because I don't remember. The initial for Austin was 465,622. Darn it, I can't remember. We're going to have to back up. For Austin, 1.03. That was my base. So times 1.03 to the X. And my population for Columbus, my population model was P of T equals 632,910 times 1.1. I don't know what was, I better look. 1.01. 1.01 to the X. So those are my two population models, okay? If I want to figure out when those are going to be equivalent, you set them equal to each other. So I want to know, when will Austin's, which is 465,622 times 1.03 to the X, equal Columbus's population, which is 632,910 times 1.01 to the X. I want to know when they're equal. So again, at this point, we don't have algebra tools, so we're going to use graphing technology. So I type in Austin for Y1, Columbus for Y2, set my window to handle it, and then calculate the intersection point, which says, when X is 15.7 and Y is 739,587.26. So what this says is, in 15.7 years, the populations should be equal. Okay? Alright, so you try this one, hit pause, come back when you're ready, and you should get 2004. And what you do is, again, they just want to know when the population of West Goma is going to equal the population of East Goma. So they gave me the two equations. All I had to do is type them in for y1 and y2 and set my window to handle it, and they intersected right there. So when x was 5.6, y would be 16.4 million people. Okay, that means in approximately, if I round, 6 years. Well, we started this in 1998. Add 6 years to that, you get 2004. Okay? All right. Bacteria growth. It says the number B of bacteria in a petri dish culture after T hours is given by this function. What was the initial number of bacteria present? Guys, remember, this doesn't look like the population model, but remember how that initial one was, that piece of knot is whatever's touching this to an exponent, that's your initial population of whatever, whether you're talking about people or bacteria. Okay, so the initial number of bacteria present was 100. And if you want to do the math, to get the initial, you would do B of 0, which would be 100 times e to the 0.693 times 0. That would be 100 times e to the 0. That would be 100 times 1, which would be 100. I mean, you can do the math if you want, but it always works out. B says, how many bacteria are present after 6 hours? They're giving me a time of 6. So if I plug in 6, I get 100 e to the 0.693 times 6. Okay, and if I do 0.693 times 6, this is going to be 100 e to the 4.158. And then you just literally type it in the calculator. Your E key is blue divide. So you do second divide to get your E. And, oh, I just did a table of values on this. But anyway, when you type this in, I would do 100 second divide, caret 4.158, and you get 6,394.35. And just to show you, though, you could look at a table of values. So if I typed this function in, this function, and I went to table, 0 would be the beginning. There's my 100. 6 hours later, there's my 6394.4. Okay? Alright, so you do this one, hit pause, come back when you're ready. And hopefully you got number 1. If you did not, it says, there's your function, a of x equals 100 e to the negative 0.0196x, and they gave me x's time, 131. If you type that in the calculator, you get, or type the function in and use the table, you get the 7.67. Okay? Alright, so how do you identify and graph logistic growth functions? Didn't we just do that one? Yeah, we did that one. Alright, so now solving exponential functions. Now we're going to start, very slowly, learning how to get x out of the air, basically. And what you do is you're going to rewrite each equation with the same base, and then you're going to write the equation setting exponents equal to each other. And what it means is, if I gave you 2 to the x and I said it equaled 2 to the third, then x has to be 3. If you're going to claim 2 powers are equal, the only way that 2 powers are equal is if the exponents are also equal. Okay, so that's kind of the gist of what we're doing. Alright, so the trick is to make both of these bases match. And you got this fraction, and you never want fractions. So, oops, I can rewrite that as 5 to the negative first to the x. Right? Because if you take 1/5 and you move 5 back up, its exponent is a positive 1, so on top it'd be a negative 1. and on this side's 125. So now over here I have 5 to the negative x. The trick is to rewrite this side as 5 to something also. Well, break it down by 5s. By 5 is 25, by 5 is 5, so I can rewrite this as 5 cubed. It's still 125. And now that my bases match, my exponents have to, because the only way those two sides are equal is if you have matching bases and matching exponents. So I can write an equation that says negative x must equal 3. Get x alone, divide by negative 1, I get x equals negative 3. I'm done. And you could even try it. If you typed in 1/5 to the negative third, it will give you 125. Alright, so this one. Okay, again, I don't want fractions, so I'm going to rewrite this as 16 to the negative first. This base is a 2. I need to rewrite this with a base of 2. So I'm going to break down 16 by 2's. By 2 is 8, by 2 is 4, by 2 is 2. So I can rewrite 16 as 2 to the 4th. So if I rewrite, but I still have that negative 1 out there, okay? I'm just rewriting the 16, and that's going to be 2 to the 4th. But now if I distribute, that's going to be 2 to the negative 4th. And on this side, I have 2 to the 5 minus 3x. Now my bases match, so my inequalities have to be equivalent. They might not, they might not look the same, but they have to be equivalent. So I can set up an equation. 5 minus 3x has to equal negative 4. Solve it. Minus 5 minus 5. Negative 3x equals negative 9. Divide by negative 3. Divide by negative 3. X equals 3. And you can plug it back in and check it. Alright, you try this one. Hit pause. Come back when you're ready. And hopefully you got 1. If not, I don't like fractions, so that's 625 to the negative first. I want 5, so I'm going to break 625 down by 5. Goes 1, 2, 5. By 5 goes 25. By 5 goes 5. So 625 is 5 to the 4th. So I have 5 to the negative x equals, I'm going to rewrite that. Just the 625. I'm not doing anything with the exponent, and I'm going to write it as 5 to the 4th. So then I distribute, no, not distribute, power, and I get 5 to the negative 4th. So now that my bases match, my exponents have to be equivalent, so set up an equation with them. Negative x must equal negative 4, divide by negative 1, x has to equal 4. Alright. Try this one, hit pause, come back when you're ready, and hopefully you got 3. Okay, this side is base 4. So my goal is to rewrite 256 with 4's. Break it down by 4. 256 divided by 4 is 64. By 4 is 16. By 4 is 4. So I can rewrite 256 as 4 to the 4th. And now that my bases match, my exponents have to be equivalent. So I can write an equation that says 10 minus 2x has to equal 4. Minus 10 minus 10, negative 2x equals negative 6. Divide by negative 2. X has to equal 3. Cool beans? Alright, so how do you evaluate exponential expressions? That's not really what we were doing. I don't know if we were really evaluating them, but let's say to solve them, the trick is to make the bases match and then write equation where exponent equals exponent and solve for x. Alright, and that brings us to homework. So we are done. Happy homeworking, and I will see you next time.